we're starting with what's called the tangent and intersected chord theorem. It says if a tangent and a chord intersect at a point on a circle, then the measure of each angle formed is 1/2 the measure of its intercepted arc. So let's draw that real quick. Here's my circle. And so let's make this line here that's tangent at the bottom. At this point, we'll call this point A. And then I'm going to make I'm going to make a chord from A up here somewhere. We'll call that B. All right. Now what that does is that split this circle into two pieces. Okay, so this piece here, okay, so there's one arc that goes this way on the left, and then I have a different arc that goes this direction from A to B. Now, kind of the way I drew this side right here is longer, so we need to kind of insert a third point just so we can separate which one's the major arc, which one's the minor arc from our previous lessons. I'm going to call this one angle 1 and this angle 2, okay, because I have this going this way from B to A, back this way is one angle. The other angle goes from B to A in the opposite direction to the left. Okay. Now what this says is that the measure of each angle formed. So this angle 1 over here on the right, that's 1/2. So the measure of angle 1 is equal to 1/2 the intersected arc, which is going to be arc AB. Okay. Going on this left side, the measure of angle 2 is going to equal 1/2 the measure of this intercepted arc on this side. This is the major arc, so we would have to call this ACB. Okay, so this theorem tells us that this angle is half of this arc, and this angle here is half of this arc on this side. All right, let's look at what that looks like on an example. Alright, so we have these examples to look at. The given information says that line M is tangent to the circle. So this is tangent here, and this is tangent here. And we want to find the measure of either the red angle or the red arc. For this example A, I'm going to look at this angle 1. And for the example B, I'm going to look at this arc here, arc LJK. Okay, so I have this angle. And this right here, from A to B, this curve right here is 130 degrees. That's the intercepted arc. So I know that the measure of angle 1, according to the theorem we just looked at, is going to be 1/2 the measure of arc AB. And since I know that the intercepted arc is 130, that tells me that the measure of angle 1 is equal to half of 130, which is going to be 65 degrees. Okay, so now looking at example B, I noticed that they gave me the measure of the angle. And I know the angle is half the measure of the arc. So if I'm going backwards, I have to double the 125. So the measure of arc KJL is 2 times the angle, which is going to be 250 degrees. Alright, let's look at now what happens when two lines intersect a circle. Okay, now we have to assume that they're not parallel, because obviously if they were parallel they would not intersect. So let's draw some circles here. One way they can cross is if they cross inside the circle. Okay. They could also cross outside the circle here. The other possibility with it would be that they cross on the circle. Like so. So now we got to look at these theorems. So we want to look at inside the circle. So I have two chords here that are intersecting inside the circle. The theorem says that each angle measure is going to be half the measure of its intersected arc. So I do have some vertical angles. These two here would be vertical, and so obviously they're going to be equal. So I'm just going to pick one, and I'm going to call this one angle 1. And we're going to look at, so the measure of angle 1 then is going to equal 1/2 the sum of the intercepted arcs. So the intercepted arc for this part of this side of angle 1 is BC. But because of the vertical angle on this side, I have to take into account the arc AD as well. So the measure of angle 1 is equal to half of the measure of arc BC plus the measure of arc AD. So I have to add these two measures and then take half or divide by 2 to get the angle here. Now, the other set of vertical angles are these two right here. So I'm going to pick one, it doesn't matter which one, I'll just put that here, call that angle 2. Now the theorem says then that the measure of angle 2 is going to be 1/2 the sum of its intersected arcs. So I have an arc here, that would be DC. Okay. But then I also have the other intercepted arc that would be over here, and that's going to be AB, arc AB. Okay. So I would have these two arcs, I would need to add those two together, divide by 2, multiply by half, either one, to get angle 2. Alright, now we're going to talk about what the angles outside the circle. We've already talked about what happens when it's inside the circle. And we talked about in the previous lesson what happens with when it's on the circle. That was the inscribed angle. Now we got to look at the outside angles. On this one, for the outside one, there's kind of some different possibilities. So we're going to look at what happens if it's tangent and secant, 2 tangents, or 2 secants. But the formulas are still the same. What's going to happen is that we take 1/2 the difference of the intercepted arcs. So if it's on the inside, we add them. If it's on the outside, we subtract the intercepted arcs. So let's look at this first example here. So my intercepted arc is this AC, and then I have the other intercepted arc that's going to go this way at BC. So let's say the measure of angle 1 is going to equal to 1/2 the measure of angle, or not arc, arc BC minus the measure of arc AC. Okay, so I have to subtract the 2 intercepted arcs. Now for angle, for 2 tangents, I have 2 arcs. Again, I have this arc PR, okay, and then I have this arc here, PQR. Alright, so again, the measure of angle 2 is going to equal to 1/2 the difference of the intercepted arcs. So I'm still subtracting. The picture just looks slightly different, but the formula or the theorem is still the same. I'm still going to subtract the arcs. So I'm going to take the measure of arc PQR. I'm going to subtract it from the minor arc PR to get that, to get angle 2. And now we got angle 3, and that's made by 2 secants that are cutting through the circle. They're still intersecting outside, but it's the same idea, same formula, where I take the measure of angle 3, or to find the measure of angle 3, I want to take 1/2 the difference of the intercepted arcs. Now, as you can see them, I have an intercepted arc here. The other intercepted arc is this arc XY here. Alright, so I want to subtract the measure of arc XY minus the measure of arc WZ. And that's going to give me the measure of angle 3. Alright, so now let's look at these theorems with some numbers in them. This first one, the angle is inside the circle, so that means I'm going to add the intercepted arcs. So to find x, I need to take 1/2 the sum of the intercepted arcs. So I need to do 130 plus 156. Alright, that's going to give me, let's see, that would be 286. And half of 286 is 143. Okay. Now for this one, the angle is outside the circle, so that means I need to subtract the intercepted arcs. So on this one, x is going to equal 1/2 of 178 minus 76. Okay. So that's 1/2 of 102. And half of 102 is 51. Circumscribed angle is an angle whose sides are tangent to a circle, as you see in the picture. Alright, this brings us to our next theorem. It's called circumscribed angle theorem. And it says that the measure of a circumscribed angle is equal to 180 minus the measure of the central angle that intercepts the same arc. So if I have a circumscribed angle, let's draw that. That means I have something that looks like that, more or less. And I'll call this point A, call this one B, call this point D. Okay, so this is my circumscribed angle, so let's go ahead and call this. So the measure of angle ADB is going to equal 180 minus the central angle. And so the central angle here, if I draw it, would be A to C to B. Okay, so this angle, central angle ACB, shares this intercepted arc here. Okay, so the theorem says that I would take 180 minus the measure of angle ACB. Alright, the theorem says then that if I take this central angle and I subtract 180, I can find x. So if I do 180, or x equals 180 minus 135, would be 45. So x is 45. Alright, so now we look at example B. B is a little bit trickier, harder to see, because the x isn't on this central angle here. The central angle we want is EJF. Okay, but notice that E and F are the endpoints for both this angle EGF and this angle EJF, where the x is at. Okay, so what we're looking at then is that they share this arc here. All right. And remember that this angle J here, that's an inscribed angle. So if I can figure out the measure of this arc, I would take half of that to get x. Okay. So the circumscribed angle said that this 30 right here, or in order to get this 30, so to get this angle 30, I would have to do 180 minus the measure of angle EGF. Okay. Now, since I know this angle, I'm going to kind of go backwards. So what I end up doing to get this angle is that I would take the measure of angle E, or let me back up, the measure of angle EGF then is going to be 180 minus 30. Okay. And we're going backwards. So instead of subtracting this angle from 180, I'm going to subtract this angle from 180 to get this angle here. So the measure of angle EGF is 150. Okay. And because EGF is a central angle, I know that the 150 is the measure of this arc here. Okay. So the central angle and the intercepted arc are equal. Right. So in order to get x, x is going to be half of the intercepted arc, which in this case is going to be half of 150. and that is equal to 75. Alright, so here we have a word problem. It says the northern lights are bright flashes of code lights between 50 and 200 miles above Earth. A flash occurs 100 miles above Earth at point C, and we want to find the measure of arc BD, the portion of Earth from which the flash is visible. Okay, I went ahead and marked these out for you. The radius is 4,000 miles. Now from A to this point right here where it crosses the Earth's atmosphere would be 4,000. But since it's 100 miles above the Earth at point C, I need to add that extra 100 miles here. So this length of AC is 4,100 miles. Now, some other things that I know to solve this is that since this line is tangent to this radius, I know this is a 90-degree angle, and I know that on the opposite side, or on the other side, I have another right angle as well. So, because of that, I know that these two triangles are equal. And the reason I'm bringing that up is because in order for me to find this arc BD, I need to know what the central angle is here. Okay, so this line AC, the segment AC, is bisecting that angle down there at the bottom, and if I can figure out what this angle is at the bottom, I can figure out what the arc is. So what I'm going to do to solve this is I'm going to let this angle down here be x, which means this angle over here is x. Okay, but I'm just going to focus on the one on the right. Alright, so that I'm going to use a trig function, inverse trig function, to find out this angle. Since looking at this angle, this would be adjacent, this is the hypotenuse, so that tells me I'm using my cosine function, or the inverse cosine, since I'm looking for the angle. So the inverse cosine of adjacent, which is 4,000, over the hypotenuse, which is 4,100, is supposed to give me the measure of angle x. Okay, putting this in the calculator rounds out to be about 12.7 degrees. Okay, remember we're doubling it, so this is x as well. So 2 times 12.7 is going to be about 25.4 degrees, okay, which is this angle here. So the measure of angle BAD is about 25.4 degrees. Okay, and since it is a central angle, this is a central angle, that tells me that the intersected arc is the same measurement. So the measure of arc BD is also about 25.4 degrees.